సాగర్ సార్
మేడం
ఇది యూట్యూబ్ లింక్ వస్తే ఒకసారి నాకు పెట్టండి సార్. కామేశ్వర్ సార్ పెట్టి ఆ రీసోర్స్ పర్సన్ పెట్టమని చెప్దాం.
ఓకే, వచ్చింది మేడం, పంపిస్తున్నా.
ఓకే సార్. Sagar sir. Hello.
మేడం చెప్పండి.
సార్ రిసోర్స్ పర్సన్ జాయిన్ అయిన తర్వాత బ్రాడ్కాస్ట్ రిలీజ్ చేద్దాం.
అందుకే ఆపాను మేడం.
అదే అదే మెసేజ్ చేశాను. ఏంటో వాళ్ళకేదో ప్రాబ్లం మేడం. ఇట్ ఈస్ డిస్ప్లేయింగ్ వెబినార్ విల్ బి
మేడం లైవ్ ఇచ్చింది.
ఓకే ఓకే ఓకే.
అక్కర్లేదు, వాళ్ళు ఏమన్నా చేస్తారు.
Sagar sir.
Hi, good morning.
Good morning, Sasi sir.
Hi, good morning, Andy.
This is Sridevi from Department of Computer Engineering.
Hi, namaste Andy.
Sagar sir, allow the broadcast.
Okay, let me share my screen.
Sir, we will wait for 2 to 3 minutes. The participants are joining
Sure.
right now because just now only we started allowing the participants.
Sure. Yeah, let me know when you guys are ready. Okay.
Yes, pardon, sir?
Please let me know when you guys are ready. Andy.
Yes, 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 sir.
Madam, Sridev Garu,
Sir,
you can start, madam. Is that slowly
yes,
they will
sir.
join?
Yes, sir. Uh, Good morning, one and all. On behalf of Department of Computer Engineering, KL deemed to be University, I welcome all the participants. It's my privilege to introduce today's resource person, Mr. Sesidhar Saladi. Welcome, sir. Welcome to our today's webinar session. Let me introduce Mr. Sesdar Saladi. He completed his BTech graduate from JNTU and his MS VLSI from Wayne State University. He had 17 plus years of experience. He started his career as a characterization engineer in biomorphic VLSI and ESS. His staff characterization engineer in OVT and camera hardware engineer in Microsoft, camera engineer in Apple, and he has 6 years of experience with Google as a camera validation team lead and camera tech lead. Right now, he's working as a camera lead in Zoox. He had an experienced camera lead with holistic understanding of camera development lifecycle from inception to mass production. He shipped high-value cameras for Google Glass, Pixel, Nest home production lines. His areas of expertise are camera design, mapping product requirements to camera specifications, camera subcomponents, both lens, VCM, image sensor, camera manufacturing, supplier management, cross-functional leadership, factory test and calibration process, in-house validations, yield enhancements, product scaling, camera system integration, image signal processing, image quality, and people management. Once again, I welcome you, sir.
Thank you, Sridev Garu. It's an honor to present here to you and the KLC faculty staff. Good morning, everyone. How is everyone doing?
Yes, sir, fine.
That's great to hear. So I'm going to share my screen, my presentation, and we can get started. That's okay, right?
Yes, sir.
Okay. You guys can see my screen now?
Yes, sir.
All right. So yeah, I'm going to talk about cameras, artificial intelligence, and self-driving cars. So let's get a agenda. And as Sridevi Garu mentioned, I think I don't need to go into details, but these are all the products that I've been involved in. Mostly my main skill set lies in camera manufacturing, design, and development, and shipping about millions of camera parts to several different products that you see here. Some of them I can highlight and I feel really proud of are, for example, iPhone related cameras, and then Microsoft Windows Phone related cameras. And when I joined Google, I got this really very researchy opportunity to work on the really next generation product, which is called Google Glass. It's almost like 10 to 20 years ahead of what people were thinking at that time. So it was an honor to work on that. And then I worked on 4 generations of Pixel products. We call them Google Pixel. And now it's getting traction in India also a little bit. And Google Home Assistant is something like you talk to it and it'll respond to your actions, like saying, hey, Google, turn on the lights. Hey, Google, what's my calendar looking like? So my main role in that product was to develop the cameras all the way from inception to mass production. So it can and the main purpose of that is basically to respond to people's gestures. So you can interact with the device just by using your gestures. And then VR headsets also getting popular these days. Finally, last but not the least, is right now I put my foot into cameras in self-driving cars. Self-driving cars are gaining a lot of popularity worldwide, and I thought that I should basically come and explore that area. That's what I'm doing right now since the past 5 months or so, and it has been a very adventurous journey so far. So if I dive into what's our agenda going to be today, so I want to go a little bit onto how the camera works, and then
Sorry to interrupt you.
sure.
Can you please switch on your camera, sir? as we are
Sure.
telecasting this on YouTube, so we want
Yeah.
you to project.
Sure. Let me do that 1 minute. Okay. Can you see
Yes.
me now?
Yeah, yeah.
All right.
Thank you, sir. Thank you so much.
Hi.
Thank you.
Yeah.
Yes.
All right. Now going back to the presentation. Can you see my presentation also? Okay.
Thank you.
Yeah. So the agenda is going to be, let's discuss a bit of basics of cameras, and then how the camera's image signal processing works. And then, so these two will give us some basic fundamental understanding of what goes in, what is the information that's fed into the cameras, how the information is output, and based on that background knowledge, let's do a little bit of dive into the artificial neural networks in the camera space. So how the data is fed into neural networks in terms of images, and how we train them, how we extract all the valuable information out. We'll take a look at that. And then we apply this AI neural networks concepts into self-driving cars and see how self-driving cars work. How do we take those uh, normal cars and make them more make them into a self-driving car. So this is going to be my agenda. Uh, I would really appreciate if you can jump in and ask as many questions as you can. And let's have this session to be in a very interactive way. Based on my discussion with my friend Kamesh, who has recommended me for this talk, I also highlighted some potential projects that we can think of for undergraduates and maybe graduate students also. Does that sound fine for you guys?
Yes, sir. It's totally fine.
Okay. Yeah. So let's jump into the camera functionality. Anybody, or I just want to get a thought from you guys. Are there any like courses that you in your undergraduate or graduate level? I'm sorry, I did my bachelor's long time back, so I don't know the curriculum. That's why. Are there any imaging kind of courses that you have in your undergraduate and graduate in computer engineering?
Yes, sir. We do have the courses like image processing
Okay.
with the ECE people and CSE students also.
Okay. Okay. That's good.
Yes.
So you guys have some exposure. Please let me know if I'm going in the tangential direction, so we can utilize the time in a best way. Um, but to begin with, how does the camera work? So basically, it has a lens element. The purpose of the lens element is basically to observe the world information, and basically it will convert that into photons. So those photons are then coming inside of a sensing element. We call that as an image sensor. And the purpose of that image sensor is basically to absorb those photons and convert them into electrons. And then what we do is, for a particular intensity of photons that you receive, those the electrons that are converted will be stored, and those stored electrons are then converted into digital numbers by using an analog to digital converter. So this is like the core fundamental principle on how a image sensor works. Well, this is not all the this is not like the finalized version. So when we get this information, it is in very raw format, meaning the image sensors don't have the luxury of our eyes, which have like really good dynamic range and ability to differentiate really good colors and between light, low light, and highlight. So we would we would then process those raw signals, which I show in the next slide, using an image signal processor. So this is like a backend processing where you take the raw signal that's coming out of the lens and image sensor combination, and you make something like really, really pleasing to your eyes, something very close to how our eyes will see. This is the main idea of the camera. So what we do here is we take the core raw data from the image sensor. Then we do all these signal processing blocks. To explain a few, we highlight lens shading correction, white balance, then defect pixel correction, denoising, and then color interpolation. You do edge enhancement, and then you do color correction matrix. You also do contrast adjustment, gamma correction, and then eventually you get a really good pleasing picture out. Uh, so the main functionality of the image signal processor is basically to take some core raw data of charge information and convert them to something that is really, really pleasing to our eyes and very similar to what our eyes will see. So that is the main purpose of the image signal processor. Um, so if we go to the, well, any questions on this slide? Do you want me to elaborate more?
You can carry on, sir.
Yeah. Okay.
If any questions are there, I'll let you know.
Thank you.
Okay.
So let's dive into some of these signal processing blocks. So as I said, I just want this session to be a bit more interactive. So let's see if I can ask a question. Do you see any issue with the left picture? What is the issue that you guys see on the left picture, if I may ask?
It seems to be in dark mode.
Exactly. So this is what the shading correction is about. What the shading correction does, you're exactly right. So the edges of this image are like really dark. If you really point to the edges, and what the shading correction does is basically to correct this image for those dark edges and bring them up, as you can see in the left side image, sorry, right side image. So once this shading correction is done, this is auto white balance. Again, you can see a similar concept here. On the left picture, you can see the colors are not up to mark. I'm talking about the dome. And on the right picture, you can see the sky is looking blue, the dome is looking to its true colors. So this is what the auto white balance is done. And the way it is done is you actually go into the cameras and image signal processing blocks, and you basically train the blocks in such a way that you say that this patch or this particular pixels have white information. So that is actually your white, and you correct for the white. So all this is done inside the image signal processor that is discussed before. So once you have this auto white balance done, all the colors will be looking as shown in this chart. We call this as a classic color rendition chart, or the McBath chart. And this is an objective way of verifying uh, how good your colors are. So as you can see, there are 24 different patches, and out of them, the bottom row has all different white patches. So we make sure by doing this color correction, or white balance correction, we make sure that all the colors are up to the mark. Now you can ask me, we are only correcting for white. Why is the sky becoming blue? That is because of this one, next one. The auto white balance and color correction work together. While the auto white balance will correct for the whiteness, the color correction matrix is correcting for all the colors. So it basically is a mathematical transform. You take the raw image data. The raw image data contains RGB pixel values for each pixel, and then you multiply that by a color correction matrix. It's a 3x3 matrix, and based on that correction matrix, the colors that you're getting is shown on the right side. So, and I'm also showing before and after images on how you can basically enhance your colors in an image. So this is all done inside the image signal processor. Moving on. Again, this is another topic called tone mapping. The purpose of tone mapping is actually very clear if you check these images. What the tone mapping is doing is it's taking a linear response from your pixel or from your image sensor and basically applying a tone mapping curve where it will enhance the details from the low light conditions. As you can see, under the bridge, the light is low, very low, and then you can see on the left image, there's a lot of details that are being lost. Now, what the tone mapping is doing is it's taking that as an input, and then it's applying a color. It's a tone mapping transformation. So if basically X is your input and Y is your output, the tone mapping is something like Y is equal to X power some factor. Based on that, uh, you can get the image on the right side. So this is how the tone mapping works. Uh, as you can see, it gives us like amazing results. All the details in the low light conditions are enhanced. Another important function is high dynamic range. When we say high dynamic range, it's not just the low light or highlight. You need to capture the whole scene information without losing any details. So the difference between left and right pictures, as you can see very clearly, is the details on the sky are very clearly captured along with the sun and water, and also the details on the sand are clearly captured in the high dynamic range scene. This is also some kind of image signal processing. There are several ways of doing the high dynamic range imaging. And one of the very crude ways is basically to expose your camera for two different exposures and then grab the signals from those two exposures and basically combine them in an intelligent way to get information from those two images to bring up a high dynamic range image as shown in the right side. Uh, so my main idea of putting these slide together was to give you guys a perspective on what is image signal processing like in cameras, and based on that information, these are some of my thoughts on some of the projects that we can be thinking about in undergraduate level. And some of them that are listed here are implementation of camera system prototype. So basically what this means is uh, you'll you'll take a third party camera system. You basically implement all the components of that system and then write drivers for that, and then make sure you can image that, and then so that gives a very good fundamental understanding of all the how the camera system works. And I think it should be within the scope of the camera engineering related projects. And the second thought that I had was, how about if the students can implement algorithms for various of these image signal processing blocks that were discussed. There is huge amount of research that has been put together to come up with like really robust algorithms, for example, auto white balance or lens correction, color correction, tone mapping, and also dynamic range. Some of the project ideas would include like the students go and explore how these algorithms work, and then they implement these algorithms in their favorite software languages. So you basically, when I say implementation, it's basically taking some bunch of images as input and then implementing their own algorithms for all these auto white balance, different ISP blocks, and then seeing how they work. This kind of experience will give like really good understanding of how image processing works. And as you can see, the latest trend of things is to have cameras almost everywhere. So I can expect students gaining a lot of hands-on knowledge by using these kind of projects. And with all the conditions happening in China, most of the camera manufacturing and processing related jobs are going to shift towards India in the near future. So I think this gives the students a really good hands-on experience uh, in terms of gaining industry level knowledge about image signal processing. Uh, I'm moving on to the next phase of my talk. Now, please think of all these slides as core understandings of. I'm trying to bring up some core understanding so that I can explain the self-driving cars functionality in a better way. So initially we talked about cameras. Uh, we have cameras in the self-driving cars. Now self-driving cars also have this ability to capture the depth. That is, if there is an object that is at 10 meters, then the car knows that that object is exactly at the 10 meters. But how does the depth sensing work? This is basically two core. One is mathematical principle and the other one is physics. So the mathematical principle is explained on the left side. Imagine there are two set of eyes. It's basically very similar to our eyes. You have left eye and right eye. The way our eyes perceive the depth information is basically using this triangulation. So your left eye sees an object C in a particular perspective, and then your right eye also sees the same object in another parallax perspective. Now you can see that the distance can be calculated if you know the distance between your left eye and right eye, as shown in that left formula. So now think about replacing your left eye and right eye by two different cameras. You have a left camera and right camera looking at the same object, having two different parallax. And as long as you know the distance between those two cameras, you can calculate the distance of any object with very, very good precision. And the next one that is shown on the right side is basically, we call it as time of flight principle. The way it works is you send a pulse of light information to your object. So as you know, light travels at 3 into 10 power 8 meters per second. And the formula that shows here is D is equal to C times T over 2. So what that is saying is, when you pulse send the light towards an object, that light goes to the object and it gets reflected back from the object. What your camera is doing is literally measuring the time it took for the pulse light to return back. And based on that time it took to return back, we can calculate the distance of that object. This is also very good. This has a lot of traction in the current industry. And these are the two main ways of doing depth sensing. There are several other ways, but these are the two main ways that I wanted to talk about. Now, so far we went and discussed about, first one is how the camera's functionality is working, and then we went into image signal processing concepts, and also we went into a bit about depth sensing. And these are some mini project ideas for depth sensing. So one could be the implementation of this depth sensing camera system prototype, and also explore how depth sensing algorithms are implemented. So for example, how would the distance between the two cameras impact the accuracy of the depth? How does the time of flight sensors prototyping accuracy is impacted? What is how much is the pulse duration going to impact? What is the pulse light wavelength that you need to be giving? There are so many nuances that that can be explored, and there are so many research papers that are working on this on these concepts. Now, a little bit into artificial intelligence in camera space. So having grasped all these basic fundamental concepts on cameras, image signal processors, and depth sensing, how does the artificial intelligence work in camera space? On a high level, it's actually very simple. So it's basically, you have a neural network, and you feed these camera images to that neural network and train it. Literally, this is like a really laborious process. So you feed like thousands of, or maybe crores of images to this neural network, and you feed by classifying the objects in the image. So for example, if you see a cat in the image, you actually go and tell that neural network that this is cat, and you train the neural network uh, to grasp that information by using like huge amount of image data, and then the neural network learns. Now what happens is, now the neural network will become self-sufficient, meaning now if you give a very unknown image, then it can grasp the objects in that image and can be properly identified. So as you can see, the cat can be predicted as a cat, a dog can be predicted as a dog, and so on. This is the basic functionality of how Google Photos works. I'm not sure how often you guys use Google Photos app, but it has like really awesome functionality embedded into that. If you basically tell Google Photos that this is a particular person and then this is a particular object, then it basically can collect all the information related to that and give it to you in one bulk set. So it's actually pretty awesome how these neural networks are transforming the imaging industry, and it's with utmost accuracy even at really challenging conditions. Uh, Again, jumping into some of these AI related cool AI projects. Uh, there could be like humongous amount of use cases, but I just put some of them here, and I think all of these can be actually developed inside the university level by students. Object detection. So the way this one I think would work is basically you take a set of camera images and then you use some neural network engines. There are several of them in Python. There are several modules, for example. So the students can use those and then generate something like this uh, code, which can detect the objects. Like, so on the left side, it can see very clearly the image classification. All the buses or vehicles are marked in red boxes, whereas individuals are marked in blue boxes. Um, and this has tremendous amount of use in the self-driving cars, as you see in the next following slides. And on the right side, based on the situations that we have right now with COVID-19 and all that, um, this is a very good way of unifying thermal sensors along with some artificial intelligence to basically detect the temperature levels of people in a in different environments, like in work environment or in university environment. So you can basically uh, give a first analysis of what the health condition of each individual person is. Some more cool projects. Living portrait. So this is fascinating because you can actually take a portrait. The one that is shown here is a Mona Lisa portrait, and you can actually train based on several thousands of data from normal images and see that how the motion coordinates will be impacted. So, and based on that information, we can actually develop this kind of living portraits. Now the Mona Lisa actually can talk and speak and turn her head, which is pretty cool. Uh, that aside, on the right side, you can see this tracking video analytics. It shows that how many people are entering into a shopping mall, for example, and then you can easily think about several use cases for this, like human counting, planning the supplies. So, for example, if you see there's a lot of people who are interested in a particular segment of your shopping complex, then you can focus on that area. Safety, so you basically can ensure that if the number of people in a particular area are more than, then you can take a particular safety measures and so on. So the use cases are endless for this artificial intelligence merged with the camera space. So I just pointed a couple of them here. With that, I want to move into self-driving cars. And talk a little bit about self-driving cars and the why we need the self-driving cars, how they work in the next maybe 5-10 minutes. So motivations. The real big motivation for self-driving cars is to make a more safer world. As you can see, there's a lot of lives that are being lost in terms of accidents and
in terms of accidents.
yeah. And then the self-driving cars also will increase the productivity because you're actually not intending to sit in a car and drive by yourself. The car itself will drive. Um, so there is no steering, nothing. You just go inside the car, type your destination address, and then the car will just take you there magically. So if imagine if that could happen, all the productivity that you can get back, all the hours that you can get back in terms of driving in like really trafficked areas. And so this is mainly to increase the productivity and also to make more safer driving conditions. And there are several different levels of autonomy. We call that self autonomy is basically driving without any drivers. Um, there are the one that we are working on right now is a level 5 autonomy, meaning there won't be any drivers, there won't be any steerings or anything. You just go inside, type your address, and the car will drop you there. As simple as that. And as we speak, I think there are a lot of prototypes already available here. It's from our company and also from several other companies which can do this actually today. The only thing that is limiting them from going into market is collecting a lot of data and showing to the government that hey, we are ready. We are actually ready because we have so many miles with zero accidents, with no issues. So we need to collect all that data and show that to the government to get an approval. Uh, that's the status of our self-driving cars over here. But if you talk about self-driving industry in India, it's a bit different because the traffic in India is it a bit clumsy, and also we need to be a lot more smarter, or the cars need to be a lot more smarter in terms of making the driving conditions more safe. So I'll say if we can get the self-driving cars here, probably in the next few years, maybe it'll take a few more years for India, but it's going to happen. It's going to happen pretty soon. With that motivation, let's go and see how these self-driving cars work. So it's all based on what we talked before. Uh, so it has cameras which will help in detecting the objects, and it has lidars. Lidars are basically depth sensors. Um, and the main idea of using lidars is to basically calculate the depth of each and every object that is around the car. And radars, these are radars are used for special use cases where the cameras and lidars are going to fail. Like for example, if it is pitch dark, then cameras cannot see anything. That's when radars can be used for detecting the objects. um, so how is this functionality working? On the left side, what you see here is a depth map. A depth map is a point cloud of information. So if you remember a couple of slides back, we discussed about sending a pulse light and getting that reflected light black and measuring the depth of that object. So the lidars, the way lidars are working is they're spinning in front of the car, and they are sending these millions of light pulses for every second, and which get reflected back from those objects. And based on that reflected back light, they're trying to calculate the depth of each and every object, and that's how this depth map is calculated. However, lidars do not have the intelligence of detecting the objects, meaning lidar can say that hey, there's something at a particular 10-meter distance, but it cannot classify it. That's where all the cameras come into picture, which is shown in the right side. So as you can see in the bottom right corner, there's a vehicle that is driving, and what the cameras are doing here is cameras combined with artificial intelligence are basically detecting the objects. So it's saying that there are cars on the left side that are colored pink, and then there are some non-moving objects. There are pedestrians. All these are classified, and this information, along with the depth information that is coming from the lidar, will be used by the self-driving car to make some intelligent decisions. So now the car actually can see all the 360-degree view of its space, along with some of the blind spots, like even we cannot see, the car can see, the self-driving car can see. So using all this information, the car is trying to predict what needs to be done in the next second, in the next microsecond, and also in the next minute. So all this information is actually constantly processed. All information is constantly fed back to a big artificial intelligence neural network, which will then classify. And then there's a point cloud combined with this image processing data that gives you the top right image or top right video. Uh, Based on this information, the car can very accurately judge what it needs to do, how to overtake the vehicles, how to look at the pedestrians, where are all the stop signs, where are all the traffic lights, what it should be doing when it sees a red traffic light, how it should be making a right turn, how it should be making a left turn. All this information is actually uh, uh, is trained to the self-driving car. And the way this is done is basically you literally, this is very laborious process. You literally go into each city, each street, and you basically map all that information. So basically you drive around. For example, if I need to drive in Vijayawada, then I go to each and every street in Vijayawada, and then I map all that data. Like, then it definitely knows where, but for example, where KLC is, where how what are all the streets that it needs to pass through KLC. All this data is mapped into the car vehicle's memory. And also it's already classified, meaning if I'm going from my house to KLC, what are all the stop signs, what are all the roads that I need to go, where are all the stop signs, what are all the things that I need to pass through. So all this information is fed into the car, and the car learns and it adapts. That's how the self-driving cars work. So in a gist, this is how they work. uh, this picture is showing our prototype model that we've been working on, and it's basically it's going in San Francisco as we speak. As you can see, there are like several different cameras. You can see from the top, if you can follow my arrow, the cameras that are shown here are like they're covering the 360-degree view. And then the ones that I'm pointing right now, those are the lidars that are spinning, that are pulsing infrared light and gathering depth information. And there are several of them. You can see like 3 of them right here, or 4 of them. So all these work in conjunction to make the self-driving cars move. And it's a pretty complex system, but it's actually very fascinating. And it also all boils down to the concepts that we just discussed. So I mean, this might be a little bit advanced, but what are some mini project ideas in terms of self-driving cars? You can explore the functionality of some off-the-shelf lidars. And then uh, how are these object detection algorithms implemented? There are several different ways of implementation of this camera data. How are all these object detection algorithms working? Develop these algorithms for different object detections. So, for example, students can work on classifying traffic lights, stop signs, and then pedestrians, and then algorithms for implementing car functionalities, like what should we do if we see a red traffic light? We need to stop. So how do we implement this functionality? When can a car overtake another vehicle? And what shall it do when pedestrians are walking, and so on. So there are like several different use cases that can be explored, but all these will boil down to getting those fundamentals right, where you understand how the image processing works, how the AI works, and then how the neural network works, and then boiling down all this information and making some sense out of it, and then taking it from there. Uh, so to end it, I'm actually a camera hardware engineer, but these are some of the things that I've been familiar with. I don't work on software on an everyday basis, but these are some of the things that I think that the students need. On the software side, if they need to have some very good extensive skill set in Python or C++ or MATLAB. And then In terms of hardware, for example, we talked about some prototyping of camera systems. There are third parties who are working on these camera system boards like Leopard Imaging, Econ System, DigiKeys, and there are a lot of other uh, suppliers even in India and also. Uh, and in terms of Python AI modules, I'm very familiar with TensorFlow, for example. There are modules from OpenCV, Keras, Image AI. All these are all Python AI modules that can give you a good head start on anything that is related to AI. So basically, feeding the image and using these modules will give you a good jump start on different functionalities that we just discussed. So I think that's the end of my presentation. Uh, and I also want to thank you, all the faculty members, for giving me this opportunity, and also a special thanks to my friend Kamesh, who actually uh, gave me this opportunity to come and talk with you guys on the webinar. Thank you very much. Now I think I'll take some questions.
Uh, yes, sir. Thank you so much for giving a very really valuable information for us as a faculty who are right now going for research. There are you had given some tips or some mini project ideas also for us, so that we can take it up and move forward for our research purpose.
Sure.
Sir, here we are having some questions in question and answer section.
Yeah, let me see.
Yes, sir.
Which software is used in self-driving cars? That's the first question. Yeah, I would not restrain myself to one particular software, but we extensively use Python in our company. Is there any existing projects using AI? Yeah, I think this question probably a little bit was already answered. What do you think? Basically, the mini project ideas are all based on AI. I mean, the AI projects in terms of camera space are like humongous. They're like unlimited right now. And I just quoted like maybe 4 or 5 of them. For example, I think it would be a very good project for someone who is interested, would be to just implement the AI. So you basically take a camera into a crowded space. For example, let's say you want to know how many people are entering into your library. Uh, so I would say the easiest way to do is basically you take one of those third-party prototyping camera systems, you install that in your library, and you get a video stream out of it, and then use one of those Python languages to go ahead and develop a module where it can count the faces, and then you implement an algorithm to count those number of persons. So this is like a very simple way I can think of, but the use cases are like humongous, like traffic monitoring, or if you want to, and there is one more very good example that was quoted was to detect the temperature of persons going to a particular workplace or uh, a particular religious place or some other public activity. It's very easy to identify a person who is not feeling well and isolate him. And I think it's very important and useful in these kind of situations of COVID-19. Um, how to cover backside of the car in heavy traffic? Yeah, uh, good question. Uh, so you can see, let me go back to my last page. Yeah. What is not shown in this picture is there are a lot of cameras on the backside also. Basically, the cameras that you see in the front side are exactly replicated in the backside. So the car actually can see a lot more than what we can see. So in fact, the car will get a 360-degree view of everything that is in its surrounding. Uh, and some of the places like backside we can't see, and some of the places like down under this car, like for example this white line, we can't see, but the car can see all these details. So in a nutshell, the car can see everything that is within that 360-degree range, and that is seen by the cameras. Okay. Could you please explain bit LiDAR are expensive? Why can't we use camera computing itself? Yeah, very good point. LiDARs are expensive. You're right. And there is a lot of work that's being done recently to make them very less expensive. Um, the advantage of LiDAR comes from the accuracy of depth that they'll give. You can use two cameras to get the depth information, but uh, calculating the depth information by using two cameras and also by using all these triangulation methods, it doesn't work for long range. Meaning, if you want to identify a person that is like much farther away, triangulation is probably not a good way because the cameras cannot actually see those kind of details. But lidars are actually directly measuring the light that is returned from that particular object, and they're like very, very, very accurate. Um, so I mean, that's the price you need to pay for getting that accuracy, and it's actually really important to have that kind of accuracy in self-driving cars, because a few a few centimeters of distance in inaccuracy could cause a lot of issues. Like if I detect a person that is 10 meters away to be like for example 12 meters away or 20 meters away, then all your safety mechanisms are not going to kick in the right amount of time, which means it could really actually be really dangerous when you go and there's a lot of probability that you will go and hit that person. So accuracy is the main thing, and also long range is the main thing. Um, Next question: how to manage latency between the different image processing modules, which combinedly produce ultimate outcome? Again, another very good question. Um, so latency is the most important aspect, and I can definitely say though the latency that's coming from the image processing blocks is much lower than the data transfer latency. So there are the data transfer bottlenecks, meaning the transfer bottlenecks from image sensor to the image signal processor and from the image signal processor to the host computer are much more higher than the time that is needed by the image signal processing blocks also. And to name a few numbers, let's say you're operating your camera at 20 frames per second, which means you take 50 milliseconds for each frame. The image signal processing can all be done in less than few milliseconds, like 1 or 2 milliseconds. But the transfer, in order to transfer the first frame to your host processor, you need to wait for that 50 milliseconds and then 2 more milliseconds for the image processing. So as you can see, the main latency is coming from the time you needed to read that first frame out of your system. So while latency is important, I would say that improving the latency in terms of image signal processing is much lower priority. Or or the other way to put it is the image signal processing algorithms are much more mature in terms of latency. They can be done like really fast. They can be pipelined. There are a lot of blocks that can be pipelined and so on. How much is required to store the image data, or is it dynamically changing? Yep, another good question. I really like your questions. So uh, the data storage is mainly taken care of by the ISP itself. There is a RAM inside, and basically it has the capability to store about a couple of frames of buffer, and that's all is enough for the ISP to basically process all the ISP blocks. Meaning you get the raw data from the image signal processor, you store that in this ISP buffer, and intermittently, I think there is approximately 4 to 5 frames of buffer is all that is needed inside the ISP, and the ISP can handle that. When I say ISP, the ISP chip can handle that. is there any way to make students part of it? If yes, what are the requisites that students should have? Another important question, and a very good question. Um, I think what would be looked for when, for example, if I am trying to interview a fresher, what I would look for is definitely the acumen in the space. How good are your fundamentals? We're not looking for any deep experience in these aspects, but I think what would be really good to have is some exposure to artificial intelligence, and some exposure to image processing, and and maybe if you can do one of these kind of projects, I think that would like really enlighten the interviewer. He would jump in, and probably he would jump in and to give an offer. So what I would say to prospective students would be to stick to the fundamentals, understand the fundamentals really good, and uh, try to market yourself by doing one of these projects. Make sense? Um, next question. How can we place simple proposal on self-driving cars along with industry support? Yep. Uh, so this has a lot of implications, but what I would say is it's going to be very hard to begin with, meaning to get funding, because bringing cars or developing cars from bottoms up is going to take a lot of money. It's not like a software program we're writing, right? So what I would do definitely is for example, my I can tell the story of the founder of my company, and it's very inspiring. So he has started working on these self-driving cars projects almost 17 years back, while he was doing his PhD in at Stanford, and his main motivation was to win a competition, and the competition was targeted at developing an algorithm which can do object detection. So he started with that, and he developed a really cool algorithm for object detection, and then he won first prize in DARPA challenge. It's called a DARPA challenge. There his idea got inseminated, and then he started working on ideas of how to make this to the next level. And then he started approaching some investors. A lot of people have were not really interested, but eventually I think he found some of his some investors who were able to invest some money. And then he started working on a prototype, and he took almost 5 or 6 years to develop a prototype, and then things start to kick out really well. So it's not an easy thing to bring it from grounds up. I think what would be needed is and maybe an easier solution will be, like, now that the challenges have already been addressed by a lot of people here, it might be useful to basically gather that knowledge and maybe go and work with some car companies who will be interested to come and invest in India. But as I said before, I think developing this self-driving cars in India is going to be much more challenging. Is there a manual driving provision that will be included in the self-driving cars? Well, the whole purpose of self-driving cars is to not let us drive, uh, and this it's I understand the question, because I think you're thinking from safety perspective, like what will happen if the car malfunctions. Is there any way that we can take it over? And trust me, all those things are being addressed. I can't disclose a little bit more details, but all those things are being addressed, and I think we should be in a stage where we should just sit and enjoy our ride, and everything will be fine. So we don't need to think about manual driving at all in self-driving cars.
Yes, sir. Few more questions in chat box also. There is a question.
Sure.
What is the difference between AR and VR?
Yeah. Very good question. AR is augmented reality, and VR is virtual reality. So augmented reality is basically you take your space and you augment something into your space. Virtual reality is actually you're going virtually to somewhere. So augmented reality is like, uh, uh, so to give you a very good example, I don't know if you use Google Photos app. So if you go to Google Photos app, there's a function called, maybe I can show it in my phone really quickly. Yeah. So this is, I'm not sure if you can see this, but um, so what this is doing is you can input some characters into your world. Now I just input a heart into my world. It's right next to the clock. So what I'm doing here is I'm augmenting something into my world. This is called augmented reality. Virtual reality is basically, it's a different world. You just go into a different world. Um, I think in layman terms, that's how I would say. But does that make sense to you guys?
Sir, Selvakumar sir, can you ask your question directly so that you are waiting for a long period of time? Selvakumar sir?
Go ahead,
Hello?
sir.
Hello, sir. Good morning, sir.
Hi, good morning.
Yeah,
Go ahead, sir.
yeah. It's very interesting to know the few details like under self-driving cars is absolutely amazing interactions. I would like to know a few details about that's the LiDAR. That's you rightly answered it. And
Yeah.
a few years back, I saw in 2019, it's Elon Musk said like using a LiDAR in the like self-driving vehicles. It's
Mhm.
doomed. It says there are many computing levels are there.
Yep.
Instead, using a LiDAR makes it more
Mhm.
expensive. Also, for in a cloud, like
Yeah.
kind of in deeper and deeper cloud areas, the sliders fails to compute their
Yeah.
process.
Yep.
So you've been working on many international companies like on the self-driving cars. How do you feel using a lidar in a real environments?
Mhm.
How it has been computing it? That's one question.
Yep.
The another question, like students wants to practice in the beginning level, like which simulation software is exactly suitable for the beginning level?
Sure.
Could you please
Okay.
explain, sir?
Okay.
Yeah.
Let me answer the first question, Andy. Um, so lidars, you're right. Like if there is foggy environments and there are challenging environments where there's a lot of sunlight glare, the depth accuracy is not so great. That's where our other sensing systems come into handy. Like for example, radars. Radars have ability to actually track not only the objects but also the uh, uh, elevation. So there is some hope, or there is actually a lot of hope using radars. And then uh, there's also a concept called long wave IR cameras. These radars and LWIR cameras will address the really special case needs where lidars are bound to fail. And your comment on Elon Musk thinking that lidars are expensive and not able to be productized is going to change, sir. It's true. Maybe 2-3 years back, like lidars are very expensive, but now there are a lot of companies that are jumping in and collaborating to get the pricing down. Now, for example, the lidars price has been reduced from $80,000 to almost like less than $5,000. So it's like more than 10x reduction already. Um, and I think there is a lot of debate on whether Elon Musk's idea of self-driving cars works even without any depth sensing. I think there's a lot of debate on that, and there's a lot of people who negate that. People don't agree with that, and I think the live proof is there's a lot of accidents in Teslas, for example, in challenging conditions. And Elon Musk says that he's really confident about getting a technology that does not need lidars, but we don't think that's actually possible, because you definitely need some kind of depth information, and uh, lidars are the most promising way to get that. Secondly, on the simulation question that you had, honestly, I think there is no easy way, sir, but in terms of simulations. But however, I've seen some folks who have been working on like really low priced off the shelf, using off the shelf components. They were able to generate lidars. Of course, they don't give the accuracy and range that is needed for the self-driving cars, but I think students can learn a lot by using those kind of prototypes. So, and those cost like very less amount of money, less than $100, for example. If you want to build a lidar that just works, if you forget about the accuracy, but if you want to just get some hands-on experience to build a lidar, you can build it in less than $100. I can point you guys to some links, because I know it should be somewhere in YouTube or somewhere in my bookmarks. I know that. I think that would definitely serve the purpose. And another easy way to get into this is basically to get a hands-on internship, or maybe get into a project that a company is working on.
Mr. Shashidhar? Yeah, this is Dr. Kameshwar.
Hello,
Hello.
Dr. Kameshwar. Go ahead.
Yeah, sir. Sir, yeah, please can you share us the mini project ideas with the description? Yeah, particularly focusing on artificial intelligence and the tools what you have mentioned, like TensorFlow, Keras, Image AI, so that we can incorporate them in our course.
Definitely.
Especially for the final years.
Yep.
The real-time access. Yeah.
No, sure. So what I'll do is, I think Kamesh has the presentation already, so I can share some more details with him in the next few days, uh, with uh, with with maybe a couple of, or maybe like, I think I can materialize most of these projects, like give you more details on what are the things.
Yeah, the description is more. We need the description in terms of what student can do, what are the different modules they have to work on.
Sure.
So on and so on.
No, totally. Yeah.
Sir, one last question in a chat box. Which year self-driving car in India for commercial purpose?
Yeah. So we are actually planning to get the self-driving cars here by sometime next year. Sometime in next year, the cars will be available in the market, but it won't be like it will be driving people around. We will be putting the cars into market for collecting the data. I mean, not these prototypes that I was talking about. It's the actual self-driving car without any steerings, or it's just it'll be literally like a self-driving car. And then starting from there, maybe it'll take a couple more years to make it like really productized. So the plan, at least for the self-driving companies here, is to replace, for example, Uber. So imagine if you can replace all the Uber cars that are driving with the self-driving cars. That itself brings us a lot of revenue. So that is a couple of years away. And I think if you need to address the challenges in India, we need to be working on them right now. I mean, the reason is the traffic rules in India are much more relaxed, and we need to first ensure that all the traffic rules are correctly followed, because otherwise there is no ground zero scenario. The ground zero scenario is all people are following traffic lights, or all people are following the traffic rules. So if that ground zero scenario is established, then after we implement the self-driving cars here, I think it probably takes another year or so to get into India. But as of now, that scenario looks a bit far away. Maybe I would say 10 more years at least.
Okay. So that's all the questions are all about, sir.
Awesome. Yeah.
So I think it's a time to wind up the session.
All
I
right.
don't think
Okay.
I
Okay.
don't think so. No more questions are there in question and answer session or in chat box. So let
Okay.
me thank and wind up the session. So it's my privilege to thank my management, Dr. Koneru Satyanarayan Garu, for encouraging us to arrange such wonderful sessions from abroad people also. I would like to thank my management and for giving us all the privileges to host the sessions. Uh, Sir, before that, one more question from the student.
Sure.
Sir, what will be free open source software other than MATLAB used for simulation?
Yeah. If you're talking about AI, I think Python is a very good language, Andy. You should be, and most of the MATLAB functionality is actually in Python also. You just need to find the proper modules. A lot of image signal processing modules are available in Python. So I would definitely dive into Python if you don't want to use the MATLAB. OpenCV is one module that I used recently. It has a lot of functionality in terms of image processing. You can do like what you can do in MATLAB in like 10 lines of code. You can actually do it in like just one line in Python. It's very well organized, and a lot of people have been contributing. So I would definitely dive into Python. Actually, you don't need MATLAB, I would say.
Okay, sir. So finally, I would like one more question is there.
Sure.
Like if I open model files in Python environment, what are the software I need? Dot
Okay.
model files, I think.
Dot model. Is I think the dot model file is something very specific to a particular module, and I think you probably need to have those imported modules. I'm actually not very sure about what dot model file you're talking about, but as long as you have the proper Python modules imported into your code, it should work. And I'll let me research on this, and maybe I can get back with a proper answer.
Dot MNC, sir, medical image document file.
Okay, I see. Yeah. Okay, that makes sense. I think for that probably you need a separate module. It doesn't look like a regular image format, and hopefully it's not a proprietary file extension, meaning someone wrote in a proprietary format and they didn't do an open source for that. It could very well be possible that .mnc, but I would definitely research into more modules and see which module can open those .mnc files.
Yes, sir. That's all for today. So I would like to
Awesome.
thank our Vice Chancellor, Sir Dr. L.S.S. Reddy Garu, our Principal Dr. K. Subbarao Garu, our Registrar Sir for giving all such encouragement to arrange such wonderful sessions. And not last but not the least, our backbone, our HOD Sir Dr. M. Sivaganga Prasad Garu for encouraging us, all the faculty to do such wonderful webinars and all the participants who had very interestingly attended the entire session. And finally, I would like to thank you, Sir Sheshidhar Garu, for sparing this much of time with us and providing valuable information. And as you promised, you are going to give a good curriculum for our students also
Sure,
with the
Andy.
industrial perspective. Thank you so much, sir.
Sure, Andy. Thank you so much. And yeah, it's my privilege to come and talk to you guys. I hope this is helpful, and looking forward to have more of these in future. Thank you very much.
Yes, sir. Thank you. Thank you so much, sir.